Now let's see a few examples. Let's say G is a group that is not this. That means there are more elements than the identity element. Then there are at least two homomorphisms from G2 itself. Okay, let's see. First example is, so let's see. If f, okay, for all x in G, let f of x be equal to E. Then this is a homomorphism, and you should check that, right? And so to show this is a homomorphism, let's see. So f of xy is equal to E, right? Because xy is an element of G, and any element of G is mapped to E. And since by definition this is this, so this is equal to f of x and f of y. So therefore, this f defined in this way is a homomorphism. And another homomorphism is for all elements x in G, we can define G of x equal to x. This is a homomorphism, right? Because let's say G of xy is equal to xy, but x is equal to f of x, y is equal to f of y. Therefore, sorry, it's not f, it's G. G of x and G of y. So this G is a homomorphism. And there can be more homomorphism than this, depending on the number of elements of G. But at least these two are homomorphisms. And the next example, let's say G is a cyclic group of order 4. Let's see, e.g. generated by A, so a squared, a cubed, and a to the power of 4 is equal to eg. Okay, so the order of a is 4. And another cyclic group of order 2, e, h, and generated by b. Okay, and b squared is equal to eh. Then let's define a mapping from G to H by the following rules. So f of EG is equal to EH, and f of A is equal to B, and f of A squared is equal to EH, and f of A cubed is equal to B. So for every element of G, we have a corresponding element in H, either EH or B. And this F is a homomorphism. To check this, we just consider all pairs in G. So for example, f of let's see, non-trivial one is a times a squared, let's say. So this is f of a cubed, so a times a squared is a cubed, and by the definition of f, this is equal to b. Okay, now f of a is b, and f of a squared is eh. So f of a times f of a squared is equal to b times eh, which is equal to b, which is equal to this. And you can do this similar calculation for every pair in G, and that will show us that this F is indeed a homomorphism. And another example, consider complex numbers except for 0 and real numbers except for 0. And consider these as multiplicative groups. So we consider multiplication between complex numbers in this and multiplication between real numbers in this set. Then let's define a mapping from non-zero complex numbers to non-zero real numbers by this. So every element of complex number, every complex number is mapped to its modulus. Okay, then this is a homomorphism. So the product of two complex numbers is mapped to the modulus of that product by this mapping, but this is equal to the product of moduli, which is f of z1 times f of z2. So therefore this f is a homomorphism. And next, consider this group defined by this Cayley table. This is a non-abelian group of order 6, so there are 6 elements. And let's define a mapping from, so let's call this group G, from G to the set of two integers, -1 and 1, okay, by the following rule. So P of E is 1, P of A is 1, P of B is 1. And P of C is -1, and P of D is -1, and P of F is -1. And the mapping defined by this is a homomorphism from G to this set. And you should verify this. For example, P of AB is, so A times B is E. And by this rule, this is equal to 1. And P of A times P of B. So P of A is 1, P of B is 1. So 1 times 1 is equal to 1. So they are equal. So this is okay. And you can do this for all pairs of elements of G. Let's pick another example. Let's say P of B, C. Okay, B times C is F. So P of F, which is -1, according to this rule. And P of B times P of C. So P of B is 1, P of C is -1, which is -1. So they are equal. So in this way, you can verify all of the pairs and show that this mapping P is indeed a homomorphism. Next example, consider this set of 2 by 2 matrices. This is a set of 2 by 2 matrices that has this form, x, y, 0, t, where x, y, t are real numbers, and xt is non-zero. Okay, and you should first show that this is a group. So you should show this set of matrices satisfies all the axioms of the group. And let's define a mapping F from G to non-zero real numbers by the following. So F of x, y, 0, t is mapped to xt. Okay, of course, because of this definition, this is non-zero, by the way. And you should show that this is a homomorphism. Okay. And the next example is the general linear group of 2 by 2 matrices over real numbers. And this is a group, as we have seen before. And we can define a mapping F from GL to R to real numbers by this. So for any 2 by 2 matrix belonging to this group is mapped to its determinant. Okay, and this is a homomorphism. And as you can see easily, so if we consider the mapping of image of AB, that is the determinant of this matrix product. But as we have learned in linear algebra, the determinant of a product is the product of the determinants, right? So that AB is that A times that B. So in fact, this mapping is a homomorphism. One of the reasons to study a homomorphism is to learn more about the structure of a group involved in the homomorphism. For example, suppose G is a group. So, nothing else is assumed other than it is a group. Okay? And suppose there is a homomorphism from G to G. So this is an assumption. Okay? Homomorphism defined by this. F of x is x inverse. Okay? Then f xy is by definition xy inverse, and that is y inverse x inverse. Okay, but since f is assumed to be a homomorphism, this is equal to f of x times f of y, which is equal to x inverse times y inverse. But this is, so therefore this is equal to this, right? So we have y inverse x inverse is equal to x inverse y inverse. And from this, we can conclude that xy is equal to yx. Okay? So this means, although we didn't assume anything else about G other than it is a group, by the very existence of a homomorphism defined by this, we can conclude that any pair of elements of group G commute. So in other words, G is an abelian group. So the very existence of such a homomorphism imposes this very strong condition on the group G.